Okay, yeah, thanks everyone for being here. Today is our second MagNet Challenge Town Hall meeting. And the purpose of this meeting is to allow the participant teams to openly share their experience with the challenge, and also we can discuss about the strategies that worked and the strategies that didn't work well, because usually we're more interested in what doesn't work than what has worked. We're welcoming all of the questions and comments from all the teams. Right now, everything is transparent, and we're happy to talk about the strategies and results. Really, this is the starting point of the MagNet community. So yeah, without too much delay, maybe we can start from the research teams. Today we have Zhejiang University International from China, University of Paderborn from Germany, Tsinghua University from China, National Taiwan University of Technology from Taiwan, Mondragon University from Spain, Southeastern University, Ming Chen Ting from China, Hangzhou Dianzi University from China, and CU Boulder from United States. So maybe let's start from Zhejiang University International. Hello, Inan. Are you there? Okay, great. Yeah.
Hello, everyone. My name is Yinan Yao from Zhejiang University, ZJUI Institute. The topic I want to discuss today is the PIN-based data-driven magnetic loss modeling. And before my introduction to our design, please allow me to introduce where are we from and our team. We are from the Zhejiang University International Campus. Our campus is in Haining City, not Hangzhou, but the city is close to both Hangzhou and Shanghai. And we have a very beautiful campus, which is in Chinese and Western combined style. Our institute, ZJUI Institute, is a joint institute between Zhejiang University and UIUC. We have 4 majors and over 1,000 students, 45 full-time faculties, 50% of them are non-Chinese. Our team has Professor Chushan Li as faculty mentor to provide guidance for us. And we have 5 student team members with 1 master, 1 PhD, and 3 bachelor students majoring in power electronics, artificial intelligence, and electrical engineering. First, let me briefly introduce some background. Magnetic components are essential power electronic devices for energy storage, energy conversion, and electrical isolation. Typical magnetic components occupy a significant portion of the volume and losses in power electronic systems. Therefore, magnetic component design plays a crucial role in power electronic system design. Accurate core loss modeling is critical for material selection, thermal design, performance prediction, and system optimization. Magnetic material loss modeling is challenging as it is a highly nonlinear system with multiple influencing factors coupling together. Factors include DC bias, frequency, magnetic flux density, waveform temperature, etc. And data-driven methods have been considered as an effective means to solve this challenge, as they have been proved to be extremely good at solving nonlinear multivariable problem. Data-driven methods typically requires thousands of parameters, large-scale data for training, high data quality, suitable network structure for specific problem solving. And due to the limitations in pure data-driven methods, as we mentioned before, we have opted to incorporate physics information to assist in model training. And the physics-informed neural network combines neural networks with physical constraints to effectively assist in learning and reduce the data dependency of neural network. We will adopt the core idea of PINN and utilize the improved general Stamets formula as the key equation. As the figure illustrates, the IGIC formula is embedded into the neural network's learning process by modifying the loss function and adding physics-related penalty terms. And the improved general Stamets equation is the most commonly used empirical formula for magnetic losses. which calculates core losses under arbitrary waveforms. Therefore, we choose IGSE as the key formula to constrain the input and output relationship. The derivation is shown here. First, core loss calculation is done. For sinusoidal excitation, we all know it is very straightforward. For piecewise linear excitation like trapezoidal and triangular wave, the derivation is shown here, in which delta Bn is the change of magnetic flux density, and Dn are the duty cycle of each segment in a piecewise linear waveform. Secondly, gradient calculations between power loss and frequency and flux density can be derived for both sinusoidal wave and piecewise linear wave. The block diagram shows how the IGSE formula is embedded in the neural network. As you can see, two parts contribute to the loss function. One is the physical constraints, as we discussed before, and the other comes from the NN prediction label error. The physics-related penalty term can be obtained by network's automatic differentiation, and also by the Stamets parameters fitting process. To verify the effectiveness of the PIN model, the normal NN model that has no embedded physics information is trained and tested for comparison. The figure shows the average relative errors of N87 material with different amount of data for training, ranging from 25 to 1600. The error results are averaged over 10 trials to avoid randomness. The IGSE incorporated PIN has much lower relative error when the amount of data points available for training is small. This observation suggests that IGSE embedded PIN enhances the efficient utilization of data. And after discussing the key idea of physics-informed neural network, next I would discuss about our network structure that is a unified framework. We proposed a physics-informed GRU combined with FNN structure. It contains two stages. One is GRU to process sequential information, BT, and the second is FNN to process T log F log B delta B, and the physics-related terms are shown here. Our structure can handle arbitrary waveforms, incorporate temperature into framework, and also integrate physical information into neural network. To verify the effectiveness of our proposed model, we compared the performance of our model and the transformer model proposed that provided by Princeton. The model is trained and tested under all types of waveforms and at all temperature conditions for an H7 material. It can be concluded that the proposed model reaches higher accuracy with a compact model size. And after introducing our proposed model, we want to discuss the model evaluation and final test results. In the final test stage, we also did some data dependency exploration experiments. The figure shows experiments conducted on material A with varying data amounts from 25 to 2400 and average over 10 trials. Notably, the normal NN model without physics information requires over 300 data points for acceptable performance, while our PIN achieves comparable accuracy with just 25 data points. The results show the proposed PIN model helps enhance the effective utilization of data by neural networks. And using our proposed model, we obtained the final results for the 5 new materials. This table summarizes our accuracy given the testing data you provide. Well, there's still a lot of future improvements can be done, including we can improve our generalizability of our model And also maybe there's a better way for incorporating physics information, and like other physics formulas can also be explored. That's our presentation. Thank you.
Yeah, very nice, Ina. I really like this method because when we were thinking about it, we were also thinking because one weakness of a neural network approach is you can't predict what's going to happen. Right? It may do crazy things beyond the training data, and if you use IGSE like what you guys doing, you can bound the result. It can't be too bad. You won't be going crazy. So that's why we really like this method, and also we like the way you presented this method can greatly reduce the number of data that you need, because in the end, if you go with IGSE, that's only 3 parameters. So you can greatly benefit from the reduced data size. So in terms of performance, the material 1 ABC looks good. Looks like the material E, usually most teams didn't do well for material D because the way it is constructed. And then E, I think maybe there are some small tuning or small adjustment you can do to greatly improve the performance for E. Because for E, I can imagine why your model didn't perform well for E, because E is frequency and flux density challenge, meaning we didn't provide some data for some frequency range, and statement equation based parameters method may be very sensitive to missing data in flux density and frequency. So that's probably where things are. So I would say very interesting method, and as you said, like there are maybe a lot of low hanging fruits to improve the model quickly, rapidly. Very good. Are you a grad student or undergrad?
Graduate student.
You're a grad student. I see. Good. Great. So Haran, Shukai, do you have any comments?
Not really. Pretty clear to me. I think it's a good idea to combine the FGSU with the neural network, and just as you said, using a physics model to bound the result of the neural network is a pretty good idea, I think.
Right. Yeah. Any comments from the audience? From other teams? Or anyone have tried or similar like hybrid? Usually we can divide the method into pure data-driven, hybrid analytical, and data-driven, and pure equation.
Hello.
Yeah, go ahead, Ray. Yeah.
I tried PINN before, but not in the MagNet challenge. It is very hard to converge. Have you solved this problem?
What do you mean by converge?
Just you see the
you know, the loss curve, it should converge. Do you mean by that?
Yes.
Yeah, we initially we countered that problem, and we found that it is because the physics related term coefficients, you can try some you can tuning your physics related terms coefficients. Maybe that can help.
Oh, okay. Thank you.
You're welcome.
Great.
So
yeah, this is very interesting.
Actually, you need to. I think the problem is that you need to decrease the coefficient gradually. You should not keep the coefficient to be constant. So after several round of learning, the coefficient should decreasing, and finally it becomes 0.
Yes, we use the exponential decay on the physics related term.
Yeah, great. Yeah, so I think this kind of method will really shine if we try to create some crazy scenario. For example, we only provide data at very low frequency, but now we are asking you to predict result at very high frequency. And a physics-based model probably will win over other like pure data-driven models. But we don't have that kind of challenge this time. Great. Yeah, thank you, Ina. If we don't have other question, we can move on to the second team, Paderborn University from Germany.